Okay, here's a couple of questions I want to think about. You may have seen before that sort of anything to the zeroth power is one, right? So in fact, I have here 5 to the 0 equals 1, but you could write n to the 0 equals 1 for n not equal to 0. And the same thing, I use 5 because it's concrete and I like think about numbers instead of letters anytime I can. Similarly, why does 5 to the -1 power? Why is that the same thing as 1/5? And again, this could be, I could replace 5 with n and say 1 over n. And again, we always want to avoid n equals 0. You can see how there could be problems with both of these if n was 0. But these are general statements you may have seen before. My real question is why? Why does this have to be the case? It's kind of a, sometimes in math, you learn these rules and you just kind of memorize them, but we always want to probe deeper. The rules come from somewhere. They really are natural. There really is like, there's some sense in which 5 to the 0 can't be any other value except for 1. And that's what I'm hoping to capture in this video, like why that's true. So if we want to get into this for a second, let's think about this. So what I guess we want to talk about first maybe is what does like 5 to the 4th power mean, right? So if we have like the 4th power, maybe start with something extremely concrete like this, right? 5 to the 4th, well, that's the same thing as 5 times 5 times 5 times 5, right? It's just 5 multiplied by itself. Well, 5 copies of 4 multiplied together. It's going to say 5 multiplied by itself 4 times, but then does that mean it's 4 multiplications? Anyways, let me say, look, the most careful way I can say it is 4 copies of 5 multiplied together. Okay, and that's some number. It turns out to be 625, but that's actually not that important. It's really just 5 to the 4th. But let's start going down. If we have like the 3rd power. Okay, so 5 cubed. Well, that's 5 times 5 times 5, and that happens to be, if you multiply that out, it happens to be 125. The square, the 2nd power, remember this is also called the cube. The square, the 2nd power. Okay, this gets, I'm somehow making this easier as we go. 5, just 5 times 5, which is 25. And then you can even say the 1st power, although some people think that's kind of strange, but why would you write the power at all if it's the 1st power? But, we can sort of see why, actually, if you kind of look down this list, why it might be nice, why this sort of makes sense, right? There's 4 5s here, there's 3 5s here, there's 2 5s here, and there's 1 5 here. Okay, and then you might say, well, now what about the 0th power? What are we going to say here? So 0th power. Well, 5 to the 0. Okay, but the problem is there's no 5s anymore. Somehow it's multiply no 5s together. And there's actually lots of reasons why it's a good idea to make that 1. But I just want to kind of see one specific reason why here. And one thing to think about is, let's think about how we move up and down this list, right, of numbers, of powers. So for example, to go from, say, 5 to 5 squared, what do we do? Well, we just multiply by 5, right? We're just adding another 5. And to go from 5 squared to 5 cubed, we multiply by 5. And to go from 5 cubed to 5 to the 4th, we multiply by 5. At each point, we're just adding a 5. So there's this extra 5 that shows up. Okay, well then what I think it's natural to ask is, what about going back down the list? So if we want to go from 5 to the 4th to 5 cubed, well, what are we going to do in this case? Really, we're going to divide by 5, right? And to go from 5 cubed to 5 squared, we're going to divide by 5. It's kind of undoing. And you can see you're getting rid of a 5, right? If you go from here to here, one of these 5s goes away. So we're dividing by 5. You can say multiplying by 1/5 too, if you prefer. And then the same thing here, divide by 5. Okay, so now we have this big question mark, which is, what is 5 to the 0? But if you follow the pattern, that's the thing, that's the part of math that is natural, that it's like somehow we're just trying to pattern match, and we want to be able to sort of, you know, when you have a positive integer power, like 1, 2, 3, or 4, it totally makes sense, right? It's just how many copies of 5 you're multiplying together. When you have the 3 here, that just says 3 5s. But so 5 to the 0 is kind of strange, but look, if you just think about what we're doing here, right? If I keep this pattern on the right going, times 5 going up, divided by 5 going down, well, what number do I need to put right here to make that work? And the answer is clearly 1, right? 1 is the number that's going to make this work, because 1 times 5 is 5. 5 divided by 5 is 1. And so that's really that's the reason why 5 to the 0 is 1. It's not any really more deep than that. Again, there's other explanations you can give that somehow there's some reason why a product of nothing should be 1. So this is like no 5s multiplied together. I don't know. It's kind of a strange thing to write or say, but in fact, I feel like I should put a big question mark or something over that, because it's like, well, what does that even mean? And there's ways to make sense of that. But look, if you just follow the table, then it gives you an answer. And then, okay, let's just keep going. What about the negative first power? Even to say the negative first anything is strange. But the negative first power, well, okay, same game. And you can sort of see it. I think you probably see where this is going now. Times 5 that way, divided by 5 this way. If we take 1 and we divide by 5, well, you have to get 1/5. I'm not even going to try to think about what it means to have -1/5s, because that's where you start to lose the sense of it. It's almost like up here, again, the exponents are sensible, but then you're going to have some sort of different interpretation when you get down here, because there's no such thing as -1/5s that you can put together. Or maybe there is. Again, there's actually ways to, you can sort of, it's kind of fun to be creative and try to think about a sense in which having like -1/5 is the same as having 1/5. Because having 1/5 is like multiplying by 5. Having +1/5, right? It's like multiplying by 5. So having -1/5 is like multiplying 1/5. You know, there's ways to interpret it. But here, it's just so apparent in the pattern, I think. This is what we want to see. And you can keep going, right? In fact, you could do the negative second power, might as well. And you can sort of see what starts to happen. Again, same game. You can do this forever. And right, we're going to take 1/5 and divide it by 5. What are we going to get? We're going to get 1/25, right? Which, by the way, is 1/5 squared. And so, right, so in general, you could even say that 5 to the, so I'll just say in general, five to the negative kth power is 1/5 to the k. And that's sort of that's where the negative gives you a reciprocal. Okay. And yeah, so I want to do a video next about fractional powers. I think there's some natural ways to get it why, like the 1/2 power is the square root and stuff. But I just wanted to, I really like this way of looking at why it's really forced just from any sort of pattern matching, which is what mathematics is all about. It's really sort of forced that anything to the 0th power is 1, anything to the negative first power is 1 over it. I said anything because, by the way, it really didn't matter that I used number 5 here. I could have replaced 5 with 7. I could have replaced 5 with 23. I could have replaced 5 with pi. There was nothing specific about the number 5 that made this work. So yeah, so I hope you found that illuminating, and I will stop. Thank you for listening.